Okay, so we can move on to the estimation of the population mean, total, and proportion. After we obtained the sample from the populations under systematic scheme, then we add up all the values of the samples, yi, and divide by the sample size, and that becomes our y bar under the systematic sampling scheme. And then we can say that, similar to how we did in the previous chapter, the estimated variance of y bar under systematic sampling is the finite population correction factor multiplied to s squared over n. But indeed, what we observed in the systematic sampling, there are two main things we have to be careful. First is the efficiencies of systematic sampling of the y bar, the mean. This really depends on the distribution of the populations of each of the yi. We'll talk about that in a second. And again, like the variance, if we consider we drew the systematic sample from the population, which is arranged in this way, so that's easier for us to understand. So in this case, we can only draw one sample from the population in a systematic way. So at the end of the day, we can have y2 bar obtained from the entire population. And with this y2 bar, we can't compare with the rest of the y bar because only one cluster was collected. So that is quite impossible to obtain an unbiased estimate of the variance of the y bar, like how we did in equation 5.2. So under systematic sampling, we need to estimate, or we try to think of some better way to estimate the true variance for my y bar. One of the guidelines is to assume the simple random sampling is as good as the systematic sampling. So we can use the simple random sampling estimates method like 5.2 to estimate the true value of the variance. Or we can use some other methods like this called the repeated systematic sampling, and we'll discuss about that later on, to estimate the true variance of the y bar. So let's try to prove our equation 5.1 and 2. Let's look at theoretically, we could be able to obtain different y bar from the population, and each of the y bar would have a probability being chosen of 1 over k. So the expected value of the y bar under systematic sampling would be equals to the y1 bar multiplied to its probability plus y2 bar multiplied to 1 over k. So taking 1 over k as a common factor, y1 bar is indeed the summation of the entire first row of all of the yi value divided by the sample size. And y2 bar is the entire second row and divide by the sample size, etc. So we take a common factor at 1 over n, and then we have the summation of all of the value for all of the populations. So in other words, that equals to the summation of true yi divided by nk, which is the population size, and that is a capital Y bar, which is the true value of the populations. So we just proved this is an unbiased estimator for the population mean. And theoretically, we can also obtain the distribution variance of each of the y bar. Let's say we want to compare each of the yi bar value to the true population y bar. But in this case, we can only divide by k, but not k minus 1, because we are calculating the true values of the sigma square of the y bar. So population total estimate and the variance. Like the similar to the previous chapter, then the total is indeed equals to the population n multiplied to y bar. And then the estimated variance of total is n squared multiplied to variance of y bar. Population proportion, similarly, the yi value would either be 0 or 1. And then we can draw a systematic sample from the population and obtain the unbiased estimator for the proportion for the population. So I'm going back to compare the systematic estimator y bar with a simple random sampling y bar. Because we mentioned earlier that the population distribution of all of the yi values would help us to improve the systematic sampling. For example, if we have a random population, then drawing the sample in a systematic way and drawing the sample based on a simple random sampling, they are equally efficient. So let's say if, for example, I can have a student and I have a list of students' grades on the test or on an examination, I try to put the students with the order in an alphabetical order. So since there is no reasons why some of the students at the beginning of the alphabet would have lower or higher grades, so if I draw a simple random sample from the list of the students and I draw it in a systematic way, they would be equally efficient. Why is that? We may want to refer back to the systematic sample. Okay, I like to go up a little bit on the last table of the natures of when we talk about the systematic sampling. Systematic sampling and stratified random sampling, they are two different sampling scheme. Under the stratified random sampling, we prefer that within the group or within the stratum, we want it to have smaller variance. We want them to be quite similar to each other. Whereas systematic sampling, we want a large variation within the group. And inter-cluster, we want them to be quite similar for systematic sampling. So that's why systematic sampling could be considered as a special case of the cluster sampling. That we want the sample that we drew, we want higher variation within the cluster or within the group. So if we look back into the comparison, we mentioned that if I draw the students in a systematic way, so let's say every 5 students I draw from the list, if they are listed in alphabetical orders, and since alphabetical orders doesn't have any of the names, doesn't have any effect on the grades, so drawing the students in a systematic way would be as good as a randomly drawn sample. If we compare the ordered population with a linear or monotonic trend, so either there's increasing with the list or decreasing values with the list, then a systematic sampling would be more efficient than a simple random sampling. So for example, if we look at the list of some of the values of the variables, if we know that the value is increasing, so some of the smaller, medium, and then the larger values, if I draw the sample in a systematic way, so let's say every 4th elements being drawn, then we can capture some of the smaller value, some of the medium values, and some of the larger values to be included in my sample. So this one cluster sample, we have more variance, so they are more heterogeneous within the cluster or within my systematic sample. And in this case, my sample would be more efficient than a simple random sampling. So for example, if I have a chronological listing in a bank such that the bank listing of the outstanding mortgages balance is listed. So I have a date listed and I know the mortgage outstandings, tends to have smaller balance than the newer ones, because some of the mortgage has been repaid for the older mortgages, right? So I would have, if I have a the date listed of the mortgage of the banks, if I draw the account with a systematic sample, then I can obtain a sample that have some of the smaller outstanding balance and some of the medium size of the outstanding balance and the larger size of the outstanding balance. So with the heterogeneous within the sample, I would have a more efficient sample collected. That said, the expected Y bar would be more precise to the population mean. Thirdly would be the periodic populations. So some of the data would have a cyclical trend. For example, if I'm trying to look at the spending of a grocery stores, okay, so it looks like on the weekends or weekdays data, weekends data, and weekdays weekend. So it seems that the weekend data shows a higher outstanding, higher spending. So if I draw a systematic sampling, that K value coincide with the lambda, which is the periodic cycle, it is not very ideal, because at the end of the day, I capture a list of the samples that overestimate the true value. So in this case, if I have a periodic population, we would try to find a K, the systematic sample, that would capture some of the lower values, some of the higher value, some of the values in the middle, etc. Okay, so we need to be careful with the distribution of the population itself, and to draw the systematic sample from the populations. It says the example, average daily sales volume for the chain of grocery stores. So they would have a January cyclical data with the weekends, so we are not trying to capture all of the peak values or the lower values. One way to reduce the possibility of choosing the observation from the same cyclical cycle is to have a different random starts from time to time. So let's say in the first 15 selection of the 1 in K systematic sample, we can have a random start of 2, and after 15 selections, we can change a different random start. So supposedly, after 142, we would have 152 values being chosen, but we drop the we start with another random start. So let's say 152 would be another random start between 142 and 152, and then we keep on drawing another 15 selections from the population. Then we try to avoid capturing all the same kind of the data. Okay, so fractional intervals, it's trying to deal with that. If I have the population size 940 divided by my sample, it does not come to an integer K intervals. So we suggest a fractional interval selections. Simply with our non-integer values, we multiply that by a 10 or by hundreds to come up with an integer values. So we can choose a random start between 1 to 94 instead of 1 to 9.4, right? So 1 to 94, let's say we have a random start 89, then 89 divided by 10 again, so we would have the first random start is 8, and 89 plus the 94 interval, so that the next start, the next selected item would be 183, but we need to divide by 10 again, so the next one would be 18th, etc., etc., until we come to the next selection of the we collect 100 units from the population. Okay.